Good morning, grade 11s. I'm Mr. Kgosana TG. I'm going to do a revision session with you on physical sciences. Today's topic, we are going to look at the Newton's law, and then in particular, we'll be focusing on the Newton's second law and the application of the Newton's second law. So by the end of this lesson, you should be able to be in the position to know how to differentiate between kind of forces that are acting on the horizontal plane, the vertical plane, and the inclined plane. You should also be able to differentiate between the force diagram and a free body diagram. And lastly, you should also be able to distinguish between the forces in which are acting on the horizontal plane, the vertical plane, and also an inclined plane. So, when we talk of the forces in which we are going to talk about today are the weight, the normal force, the frictional force, tension force, and the applied force. And then all those forces in which I've mentioned are the force in which they are acting on the plane, which I've also mentioned as well. So when we talk of a weight as a force, a weight, it is referred as the gravitational force the F exerts on an object on or near its surface. And then when we talk of a normal force, it is a force exerted by a surface on an object in contact with it. The frictional force, it is a force that opposes the motion of an object and it acts parallel to the surface, the object it is in contact with. Then when we talk of the Newton's second law, our Newton's second law states that when we have a net force which is acting on the object, the net force will be, when the net force acts on the object, it will cause the object to accelerate in the direction of the net force. The acceleration is directly proportional to the net force, and it is inversely proportional to the mass of the object. Then in the acceleration, because the net force also includes the mass of the object and the acceleration. When we talk of the acceleration, we'll be talking of the rate of change of velocity. So, to start off with our lesson today, we will discuss the forces in which they are acting on the horizontal plane. Suppose we have an object, and this object, it is placed horizontally on the horizontal plane. The force in which they will be acting on such object which will be on the horizontal plane, we are going to have our normal force, which the normal force will be going vertically upwards, and then we are going to have the weight, which the other term which we use for the weight is the Fg. So the weight will be going vertically downwards, and then we can have the applied force, and then the applied force in this case is going to the right, and then it is also acting horizontal or is acting parallel with the surface. Then because of the applied force, it is applied to the right. So the motion of the object will be moving to the right. Then our frictional force will be opposing the direction of the motion. Hence the frictional force will be going to the left hand side. So coming to calculations, when you are required to calculate the, let's say for example, the magnitude of our frictional force. The magnitude of the frictional force is equals to the coefficient times the normal force. And then when the kinetic friction being equals to the coefficient times the normal force, we have two types of frictional force, which we talk of a static frictional force and the kinetic frictional force. And then when we talk of the static frictional force, the static frictional force will be referring to static frictional force occurs between a stationary object and the surface in which it is resting. And then when we will be talking of the kinetic frictional force, the kinetic friction occurs between an object in moving across the surface. So when we want to calculate the magnitude of our normal force, so in the diagram, if it is placed on the horizontal plane, our normal force, where the applied force, it is applied horizontally, and then is moving, the motion is going to the right, in which is the direction of our applied force. Then our normal force in this case will be equals to the Fg, which is our weight. So normal force will be equals to Fg, and how we calculate the Fg, we say it is equals to the product of the mass times the gravitational acceleration, which is equals to 9.8 meters per second square. So here our normal force will be equals to the Fg, and our Fg is equals to mg. Then in order for us to calculate the magnitude of our kinetic frictional force, then it will be our kinetic frictional force from the equation, which it is the coefficient times the normal force. And then we just state that our normal force, when the force applied, it is applied horizontal, our normal force will be equals to the Fg. So our kinetic friction will be equals to the coefficient times the Fg. And then that will mean that we are going to take the coefficient and then we multiply it by the mg. And then the mg is the quantity in which we use to calculate our Fg. So in order for you to calculate the magnitude of the kinetic frictional force in this case, it will be that it is equals to the coefficient times the mg. Then we can have another scenario or a case where our applied force, it is not applied horizontal to the plane. So it's not applied parallel and horizontally with respect to the surface. So we can have an applied force where the applied force, it is applied at an angle with the horizontal. So when we have an applied force being applied at an angle with the horizontal, so let's say for an example, an angle being 20 degrees Celsius. So when it is 20 degrees, pardon me for including the Celsius part. So if it is 20 degrees, then your applied force, it is applied at an angle with the horizontal, which your angle, it is 20 degrees. Then if we were to draw other forces which are acting on this object, which the applied force, it is applied at an angle, we are going to have our normal force, and then we are going to have our Fg, then we are going to have our frictional force. And the direction of our normal force will also going to be vertically upwards. The direction of the Fg is going to be going vertically downwards. The direction of our frictional force will be going to the left. So when we want to calculate our normal force, in this case, we will need to consider also the component of our applied force, because our applied force, it is applied at an angle. So then we are going to talk of the horizontal component, which we call it Fx, and the vertical component, which we call it Fy. So your horizontal component will be going in the direction of the motion, which is to the right and then the vertical component will be going upwards, which it will be in the same direction as the direction of our normal force. So in this case, it means that our normal force plus our Fy, which is the vertical component, will be equals to the Fg. So the all upwards forces, they will be balanced by all the forces which they will be going down. So in this case, we have our normal force going up, our vertical component, which is our Fy, it is also going up, and then our Fg is going down. So if we want to know the magnitude of our normal force, then we will say our normal force is therefore equals to Fg minus Fy. So from the first one in which we wrote normal force plus Fy is equals to Fg. So if we want to make our normal force the subject of the formula, we are going to take the Fy, which is our vertical component, to the other side of the equal sign, and that will give us normal force being equals to Fg minus Fy, and then that is how we can able to calculate the magnitude of the normal force. And then when you go to our equation of the frictional force being equals to the coefficient times the normal. So where we see the normal force on the equation for calculating the frictional force, we are going to substitute the normal force with Fg minus Fy, and then we use the substitution where our Fg it will be mg, and our Fy it will be the force applied, the sine of the angle, and the angle in this case which is given to us, it will be 20 degrees. So we are going to have coefficient in brackets Fg minus Fy. So we have substituted our normal force with Fg minus Fy, and then we can do our calculation with respect to that equation. Then our last scenario, we can have now that applied force, it will be applied at an angle with the horizontal, but the direction of the applied force now it will be going downwards with respect to the angle given on the horizontal. So what I mean by that is that if I'm having an object still on the horizontal plane, and then I'm having the applied force, and this applied force, the direction of my applied force is going downwards at an angle with the horizontal. So in this case, my direction of the vertical component is going to change. So when we have the vertical component, it will be going downwards, and the horizontal component, which is our Fx, will be going in the direction of the motion. So in this case, we have Fy going downwards, Fx going to the right, and our force applied, it is applied at an angle with respect to the horizontal. Then we are going to have our normal force, we are going to have our Fg. Our normal force is going upwards, and our Fg is also going vertically downwards. Then, in order for us to calculate the magnitude of the normal force, the normal force is the only force in this case where it is the force which is going vertically upwards. And the forces in which they are going vertically downwards, there will be our vertical component Fy and our Fg. Then that will mean our normal force will be equals to our Fy plus our Fg, or one can write Fg plus Fy. So, in the previous example or a scenario in which we discussed, we found that when we want to calculate the magnitude of the normal force, the magnitude of the normal force was equals to the Fg minus the Fy. And then in this case now, our normal force is calculated by Fg plus Fy. So the two cases are different because of the direction of our applied force. In the previous one, direction of our applied force, it is going at an angle with the horizontal, and it is a pulling force. And then in this case, where the applied force, it is applied at an angle with the horizontal, and it is going downwards. The direction of our Fy is going down, where in the previous one, the direction of our Fy is going up. So we are saying an applied force, it can be described as a pushing or a pulling force. When an applied force, it is described as a pulling force. It is when, for an example, let's say you are standing outside the classroom and then you want to enter into the classroom. So when you open the door, you will be pulling the door towards you. So in that way, that force in which you are exerting on the door handle, that is referred as the applied force. And that type of an applied force, it will be a pulling force because you will be pulling the door towards you. And then in a case where the applied force, it is referred as a pushing force. It is when we can say you are also standing outside the classroom and then you want to close the door behind you. Then in that case, you will be pushing it in a manner that it will be closing, you will be closing that door. And then in that case, we will be saying that applied force, it is a pushing force. So an applied force can be referred as a pushing force or a pulling force, depending on a different scenario in which it will be given to you. And then also, it can be a pushing or a pulling force when we have the applied force and then it is acting horizontal with the surface. So when it is acting horizontal with the surface and it is not at an angle, then it will be a pulling force which is horizontal. And then if it is a pushing force, it will be a pushing force in which it will be from the back of the object and then pushing it in the direction at which that applied force will be applied to. So that way, our applied force, it is being a pushing force, and our applied force in this case, where it is acting horizontal and then it is going to the right, hence it is applied in front of the object, then that will be a pulling force. So here, in this case, will be a pulling force. So where are we applying this symbol diagram and the symbol calculation that we just discussed? When we're coming to the Newton's second law, our Newton's second law states that when we have a net force acting on the object, that net force will accelerate the object in the direction of the net force. And the acceleration is said to be directly proportional to the net force, and it is inversely proportional to the mass of the object. So we can now look at an example which we can use. And in the example in which I'm going to share with you this morning, it is from the DBE November papers, which are the grade 11 papers. And then I'm going to look at the question 3. And this question 3, it is from the DBE November paper, which it is for the year 2015. So we can also obtain the paper from the Google. If you can just go to Google and then you say DBE November paper grade 11 physical science, and then those papers, they must come up, and then you can be able to choose which year you want to download. So today's we are going to look at the November paper for the grade 11, which was written in the year 2015. And then if the times allows us, we are going to look at the next question, which will be in a different year, but basically we are going to I'm going to share with you the questions which are from the November paper, which is the paper you are about to write very soon. So on this question, I'm just going to read it for you, and then you will be able to obtain the question later on. I'm reading the DBE November paper, which is for the 2015. The question will be question 3. It states on the statement that a constant force F pulls a 50 kg block at a constant speed over a rough horizontal surface AB, as shown in the diagram below. The coefficient of the kinetic friction between the block and the surface is 0.4. So what we need to highlight from this statement which is given, before we can even go to the questions, our key word here, it is that we have a constant force F which pulls a 50 kg block, and it pulls this block at a constant speed. So when we have a constant speed, this tells us something with respect to the acceleration of the object. And then when we define an acceleration earlier, we said it is the rate of change in velocity. So when we say is the rate of change in velocity, we simply mean that acceleration is equals to the change in velocity over the change in time. So the rate, it implies time, dividing by time. So it's the rate of change in velocity. So, but when we are given the statement that the motion is moving at a constant speed, so this means that your velocity, because we refer a speed and a velocity having the same unit. So a speed, it is a scalar quantity which is only having the magnitude. But when we talk of the velocity, we are talking about a vector quantity which is having a magnitude and the direction. So when we calculate the acceleration, we are saying acceleration is equals to the rate of change in velocity. Then in this case, we refer from the statement given to us a speed as a velocity. So because we are given that a constant, the motion is moving at a constant speed, this will imply that the acceleration of the object will be equals to 0 meters per second square. Why is it 0 meters per second square? Because the acceleration is defined as the change in velocity. So when it's given to you that this object, it is moving at a constant velocity, for an example, then your velocity does not change. And then when your velocity is not changing, it simply means the acceleration, which will be depending on that velocity to change, will be 0 meters per second square. And then in that case, constant speed or a constant velocity will imply acceleration being 0 meters per second square. So when we move to the questions, you are further given that the coefficient is equals to 0.4. Then the question 3.1, it states that draw a labeled free body diagram showing all the forces acting on the block. And then when we draw a labeled free body diagram, we represent the object with a dot. Then you indicate the forces that are acting on that object when it is in motion. So the object is represented by a dot, and the forces which are acting on the object, they will be indicated by the arrows, and the direction of the arrow must be facing away from the dot. So we are going to have our normal force, which is going to be vertically upwards. The direction of our FG, which is going vertically downwards. The frictional force will be going to the left, and our applied force, remember our applied force in this case it is applied at an angle with respect to the horizontal. Then is going to be at that angle with the horizontal. So that will be our free body diagram for this question. So our free body diagram will be our normal force going vertically up, frictional force going to the left, Fg going vertically down, and then our applied force being at an angle with the horizontal. Then the question 3.2, it says, state the Newton's first law of motion in words. And then when we talk of the Newton's first law, our Newton's first law states that when an object it is at rest, it will remain at rest. And then when it is moving at a constant velocity, it will continue to move at that constant velocity, unless there is an external force or an unbalanced force which is going to apply on that particular object. So our Newton's law, in short, it states that an object continuing in a state of rest or a uniform velocity unless it is acted upon by an unbalanced force. So that is our Newton's first law. And then moving to the next question, to number 3.3, it says calculate the magnitude of the force F. So the magnitude of the force F, it is the magnitude of our applied force. So it can be referred as the applied force, or we can label it as force F. So in this case, what we are going to have is, we are going to use our formula for F net is equals to MA, which this is from the Newton's second law, where we say when the net force is applied on the object, it will cause the object to accelerate in the direction of the net force. The acceleration will be directly proportional to the net force, and it will be inversely proportional to the mass of the object. That is our Newton's second law. And this Newton's second law, it is according to the acceleration. Then we just discussed before that our acceleration in this case is going to be equals to 0. So if we substitute the acceleration as 0, and then the mass which is given to us was 50 kg. So it's a 50 kg mass. We multiply that mass with 0. Why are we multiplying it with 0? Because our acceleration is 0. Why our acceleration is 0? Because we are given from the statement that the motion is moving at a constant speed. So a constant speed will imply that the motion, it is moving at 0 acceleration, which is 0 meters per second square. Then this will mean that the magnitude of your net force will be equals to 0 Newton, because of our acceleration is 0. Then in calculating the magnitude of force F, which is our applied force, our net force, it is also known as equals to the sum of the forces which are acting on the object when the object it is in motion. So when we are going to represent our net force as the sum of the force, we are going to consider those horizontal component and the vertical component, because our applied force, it is applied at an angle. Then we are going to have our horizontal component Fx, which is going in the direction of the motion, which is to the right, and our vertical component, which is Fy, which is going to be going upwards or vertically up, and then it will be going in the direction of our normal force. So then our net force will be represented by those forces in which they are acting on our horizontal plane, or which are horizontal with the surface. Then those are our frictional force, which is going to the left, and our Fx, which is going to the right. And those are my horizontal forces. Why am I not talking about the normal force and the Fg? Our normal force and the Fg are the forces which are acting on a vertical plane. So in that way, if they are acting on a vertical, or if they are acting vertical, then this means that they will not be having any impact on the motion. So the forces in which they will have an impact on the motion are the ones in which we represent them when we talk of the net force. So then we say those forces in which they go in the direction of the motion. In this case, the force in which is going in the direction of the motion, it is our Fx. Then we take Fx as a positive force. So that is our positive force. And then our frictional force, because it's going to the left, then we regard frictional force as our negative force. So when we write the sum of the force which are acting on the object when it is in motion, then our F net will be equals to Fx minus the frictional force. And then when it is Fx minus the frictional force, then that must be equals to 0, because from the previous one we wrote that our F net is equals to 0 Newton. Why is it 0 Newton? Because our acceleration is 0. So Fx minus friction will be therefore equals to 0 as well. And then how we calculate our Fx, it will be the force applied, then the cos of the given angle. And our given angle in this case, it is 20 degrees. On the equation as well, is 20 degrees. Then minus, how we calculate our frictional force, we say it is coefficient times the normal force, and that will be equals to 0. Then we are going to write that coefficient times the normal force inside the brackets, because outside the brackets we have a negative sign. So we will need to later on open the brackets using that negative sign. Then now I'm having applied force being equals applied force cos of 20 degrees minus, in brackets, coefficient times normal force is equals to 0 Newton. Then in order for me to calculate, because the question is asking us about the magnitude of the force F, my normal force, I'm going to write it in terms of that force F. I'm already having force F on my part of the Fx, where Fx, we are saying it is equals to F, the cos of 20 degrees. So the F, it is the one in which I need that magnitude. And then now I need to substitute my normal force in terms of that force F. So what you do, we go to the equation, which we refer to our free body diagram. And in our free body diagram, the direction of Fy is upwards, normal force is going up, then the Fg is going down. Then it will be normal force plus Fy is equals to Fg. because normal and Fy, which is your vertical component, they are all going up, and then the Fg is going down. Then the magnitude of our normal force will therefore equals to Fg minus Fy. And Fg, we calculate Fg by mg, minus Fy, we calculate Fy using force applied, then the sine of 20 degrees. So when we have normal force being equals to mg minus force applied, the sine of 20 degrees, where you see the normal force from the previous equation, you are going to substitute that normal force with mg minus f, the sine of 20 degrees. So we are going to have the force cos of 20 minus, in brackets, mg minus force, the sine of 20 degrees. Then that will be equals to 0. So we substituted our normal force as mg minus f, the sine of 20 degrees. And outside the brackets, we should be having that coefficient. Remember, it is coefficient times normal. So it will be minus that coefficient. And then what we have here, it is representing our normal force. So that will be representing our normal force. Then we make a substitution now. Your f, you don't know, is what we are looking for. The cos of 20 minus the coefficient, you are given to be 0,4. In brackets, the mass is 50 multiplied by 9,8 minus force F, which we don't know, then the sine of 20 degrees. Close brackets, then equals to 0. So our force F is what we are looking for. So in this case, you have your force F, cos of 20 degrees minus 0,4 in brackets 50 multiplied by 9,8 minus F, then the sine of 20 degrees, we close the brackets, then we are having equals to 0 Newton. Then if you continue down with the calculation, you're supposed to have 0,9 for F minus in 0,4 in brackets 490 minus 0,3 F, close brackets, is equals to 0. So the magnitude of 50 times 9.8, it is 490, and then that is what we are going to have. Then we are going to make the part where it is that force the subject of the formula. And then by making this the subject of the formula, you multiply the 0,4 to open this bracket, and then you multiply it with that. And then the answer in which you must obtain out of making those further calculations will be our magnitude of force F being equals to 182,156 Newton. That is the magnitude of our force F. Then going to the next question, it is asking us to calculate the magnitude of the normal force. So if we want now to calculate the magnitude of our normal force, we take it from this equation which we wrote here. We said normal force is equals to mg minus F the sine of 20 degrees. And then our mg is 50 multiplied by 9,8 minus force F. We just calculated its magnitude, which is 182,156 Newton. So that will be 186,156, then the sine of 20 degrees. And then that will give us the magnitude of our normal force. And then the magnitude of our normal force will therefore be equals to 171,23 Newton. So it is 171,23 Newton. That will be the magnitude of our normal force. And then the next question, it is asking us to calculate the magnitude of the frictional force. And then the magnitude of the frictional force, we say it is frictional force is equals to coefficient times the normal. And the normal force is the force in which we just calculated, where its magnitude it is 171,23 Newton. Then you are just going to substitute your coefficient value, which is 0,4, then it's multiplying by 171,23 Newton, and that will give you the magnitude of your frictional force. And that magnitude of the frictional force, it is 171,23 Newton. I think I've made an error on the magnitude of the normal force. Our magnitude of the normal force is not supposed to be 171,23, but it's supposed to be 428,07 Newton. And then meaning that our kinetic frictional force, we are going to calculate it when being 0,4 multiplied by 428,07. And then in this case, where the magnitude of our kinetic friction will be that value of 171,23 Newton. Apology for the error which I made on the magnitude of our normal force, but the substitution in which we made previously, that one will lead you to that answer which I'm talking about now, which is this, the one for, which is the one for the normal force, which is 428,07 Newton. So the last question, it is asking us, it reads as follows. It's a statement, then it shows the diagram, and then it has a question underneath. And then on the statement it says that the same constant force F is now applied to the block over the same rough horizontal surface as before, but in the direction as shown below. And then when you look at the direction of that force applied, it is applied at an angle with the horizontal, and then it's going downwards. So in this case, our applied force, it is a pushing force, and it is acting at an angle with the horizontal. So the question says, give a reason why the block will move slower than before. So for the block to be able to move slower than before, in answering the question, which it is a 2-mark question, first you need to consider what will change when we look at our normal force. Normal force in this case will be equals to your Fy, which is your vertical component, plus the Fg. Then this means that you have increased the normal force. So the normal force will increase, and if the normal force increases, then that will increase the magnitude of your kinetic friction. So your kinetic friction will also increase. So when the kinetic friction is also increasing, let me write it properly for those. So we have normal force being increased because of the normal force in this case will be equal to Fy plus Fg. Then therefore our frictional force is also increased. So when the frictional force it is increased, this means that the motion of the object will be harder to push when the applied force it is applied in that direction. So to wrap up the lesson, we talked of the forces which are acting on the horizontal plane, and then having different scenarios where we have an applied force acting horizontally with the plane, and we have the applied force applied at an angle with respect to the horizontal. It can be a pulling force or it can be a pushing force. So go further on doing the questions like this where we apply our Newton's second law, and then also look at the questions that are on needing you to apply the force which are on the inclined plane, which we did not get enough time to look at them, and also those which are on the vertical plane. I would like to thank you all very much for this time in which I'm given to be with you, and then I wish you all the best in preparation for your final examination. Thank you.